If the four vectors a, b, c, and d represent the position vector of the point a, b, c, and d, then we need to show that the points are coplanar if and only if this particular relationship holds true. Okay, now this is a biconditional statement because of the uses of if and only if. Now that means we will need to show two things here. The first part of the proof, we will show that if the points a, b, c, and d are collinear, then it must be true. The 3a vector minus 2b vector plus c vector minus 2d vector equals the null vector. And then we're going to show the other part of the proof. The other part of the proof states if 3a vector minus 2b vector plus c vector minus 2d vector equals the null vector, then it must be true that a, b, c, and d, these 4 points are coplanar. We'll start with the first part of the proof. So we begin by assuming that a vector, b vector, c vector, and d vector are the position vectors of the points a, b, c, and d such that these 4 points are coplanar. Coplanar means they are going to lie on the same plane. Then we're going to consider some scalars. Then for some scalars, well, let's name the scalars as x, y, z, and w. We have the condition that if the points are coplanar, then we can make a combination x times a vector plus y times b vector plus z times c vector plus w times d vector. This must be equals to the null vector 0, where we have to choose x, y, z, and w in such a way such that x corresponds to the value 3, y corresponds to the value -2, z corresponds to the value +1, and d corresponds to the value -2. And the choice of the scalar values has to be very specific here. They must be non-zero, and the value of x, y, z, and w must be chosen in such a fashion such that when we take the sum x plus y plus z plus w, they must add up to 0. Now, this is done so that, which means this particular equation, that is, we have the condition that 3a vector minus 2b vector plus c vector minus 2d vector, this is going to be equals to the null vector. So I will successfully show that if a, b, c, and d are the position vectors of these 4 points, then it must be true the 3a vector minus 2b vector plus c vector minus 2d vector equals the null vector. Now, welcome to the second part of the proof. So again, we're going to consider the 4 points a, b, c, and d having the position vector a vector, b vector, c vector, and d vector. However, this time we are considering just random vectors a, b, c, and d. We're not going to say that it's coplanar what, because our goal will be to show that they are indeed coplanar. Now, this implies that we have the condition 3a vector minus b vector minus 2 times b vector plus c vector minus 2 times d vector equals to the null vector. Now what we'll do, we're going to rearrange the terms. So here on the left hand side, let's keep 3a vector added to c vector, and this is going to be equals to 2 times b vector plus d 2 times d vector. Fine. Now what we'll do, we're going to divide both sides with 4. So 3a vector plus c vector divided by 4. And on the right hand side, we have 2b vector plus 2d vector divided by 4, which means we have 3a vector plus c vector divided by, so 4 can be expressed as 3 plus 1, means exactly the same main thing. And here on the right hand side, we're going to factor out first 2 from the numerator and the denominator. So in the numerator, we only have b vector plus d vector, whereas in the denominator, we will be left with 2. So 2 can be expressed as 1 plus 1. Now, let's try to understand this. So we'll start with the left hand side of the expression. So here we have 3a vector plus c vector divided by 3 plus 1. Meaning, let's say we have the point A and then we have the point C. Now A has the position vector a vector and C has the position vector c vector. We have already defined this. Let's join point A and C with the help of a straight line. Now, if we consider some point, let's call this as the point X. Now X, let's say, divides AC in the ratio 3:1. Then the position vector of this particular point X, according to the internal section formula, will be 3a vector plus c vector over 3 plus 1. Fine. Okay, so first part is done. Then let's come to the left and right hand side of the equation. So here we'll consider 2 points. We'll consider the point B with position vector B and another point D with the position vector D. We're going to join B and D. Now this time we're going to consider another point Y on B and D such that it divides BD, the segment BD, into ratio 1:1, and the position vector of that point Y is going to be B vector plus D vector divided by 1 plus 1. But this equality sign tells us that actually X and Y coincide with each other. In other words, the line segment BD is going to pass through X of the line segment AD. Now we have two line segments AC and BD which are intersecting at the common point when we are going to call it the point X, and this is only going to be true if the points A, B, C and D lie on the same plane. In other words, we are saying that the points A, B, C and D, these 4 points are coplanar with the condition that when we started out with the condition that 3a vector minus 2b vector plus c vector minus 2d vector equals 0 vector. So we have proved the second part as well. Now since both of the two proofs are done, so ultimately we can say that if a, b, c and d vectors are the position vectors of the points a, b, c and d, then it is true that the points are coplanar if and only if this condition 3a vector minus 2b vector plus c vector minus 2d vector equals the null vector.